It's really irritating that you're so quiet. Good morning. Welcome on this wonderful, rainy, misty, foggy November day. Like only 2 more months until the sun comes back. No worries. All right. So gradually we've been making our way towards neural networks, the technology that has been completely dominating machine learning for the last decade and a bit more. And today we make this transition from linear models and so on to neural networks. And we make the connection through multilayer perceptrons or MLP for short. So we will now bring together these 2 worlds. We had looked at the logistic sigmoid I've always been drawing it in 1 dimension, but of course this works in 2 dimensions also. So if I have a 2D feature space here, then if these are homogeneous coordinates, then we have an extra component here, which is constant 1. So that means my decision threshold or my inflection point need not go right through the origin. It can be anywhere, maybe here. And then I could draw isocontours, which initially are very steep, close to this decision boundary, and then become more widely spaced. Yeah? So we have now something which is 0 here and 1 there, this kind of sigmoid. Yeah? So it works in more than the 1 dimension that we had shown. And this was developed in the late 40s, originally invented by a physicist whose name I've forgotten. And then after it was invented, understood and adopted by statisticians, and statisticians were very happy with this notion. And on the other hand, there was the perceptron. The perceptron was invented in the 50s. Maybe the most important person was Rosenblatt. He was interested in the understanding of the brain and tried to come up with a machine that could learn by itself. And he managed, and he implemented this, interestingly, on an analog computer, because digital computers were not yet widely available. And that's a bit ironic. Like, some of the first cars were electric, and then they went to a combustion engine, and now we're going back to electric. And so this first computer was analog, this first neural network computer was analog. And then, of course, things became digital. And I think they will stay digital, but nowadays people are again studying analog versions. So there's all this business of neuromorphic computing, but also people thinking about, we had an initial discussion the other week, about quantum simulators and so on. Analog devices that could model neural networks. All right, and so this approach was quickly adopted by engineers, and engineers like to make blueprints and diagrams, and so this thing here they would show like so. So we have here weights or multipliers, beta 1 and beta 2 multiplying my 2 features. And when I take the I was saying that we have homogeneous coordinates, so there is always an extra input, which is constant 1, and then we have an extra parameter multiplying this constant 1. This is called the bias in perceptrons. And so far this is beta transpose x, this thing here. So at this point in my computation, I have beta transpose x. And then, well, it goes through this sigmoid. So we have a so-called activation function. And the activation function we have here would look something like so. So if this is a coordinate system and, sorry, bad, go through 0, good, and it goes from 0 to 1 here. Okay, that would be a single perceptron, and that caused a big sensation and a big media sensation. We now have machines that can learn by themselves. Yeah, so people were blown away by this possibility, and well, this all went well for a while, but you know, with this kind of linear model, you can only model linearly separable problems. Yeah, so if we have instead a problem that looks like so. Okay, we have one class here, and we have some other class in my two-dimensional feature space. Okay, I can try and train a perceptron on this, but I will always make some errors. Okay, no matter what I do here, there will always be at least a few labels on the other side. So this particular problem here is not linearly separable, this classification problem. And so it didn't take too long for people to figure out that, yeah, perceptron is great, but it cannot even solve this. And this then led to first a pamphlet and then a book by Minsky and Papert, who were saying that, you know, it cannot even solve a problem as simple as that one. What is, you know, what good is that? And now there were two things happening at the same time. On the one hand, people did have ideas of how to combine multiple perceptrons, so how to build a multilayer perceptron, but it couldn't be trained in those days. Backprop had not yet been invented formally, and I think it's not because people were too dumb, but because the analog computer that was used to train perceptrons, this could not possibly implement something like backpropagation, even if people had had the idea. So there were practical hindrances, and then yeah, there was also much disappointment that you cannot even solve that. And this led to the first winter of connectionism. Yeah? And then neural networks were revived only in the 1980s, once backpropagation had been invented and it was possible to implement it on digital computers. And then came some next winter, and then in 2012 started the everlasting summer. All right. So, okay, a single perceptron doesn't do it, but what if we now start combining several of them? Yeah, so notably, I could have, let's say, this perceptron here, and I could have that perceptron there. And let's be electrical engineers and plot this nicely. So we have our inputs x1 and x2. And we now have 2 units. Each has its own sets of multipliers. Each has its own bias. Right, and for the sake of argument, I'm going to make the nonlinearity really simple. Yeah, so I'm going to take a perfect step function as a nonlinearity this time. Because if we take a perfect step function, we now get out a new representation here. And this representation, I'm going here to call it Z1 and Z2. This here was X1 and X2. Okay. And now we need to decide in which direction. So my nonlinearities, I need to decide if they go from 0 to 1 or if they go from -1 to +1. It doesn't matter much. I'm going to let them go from 0 to 1. Yeah, so here we have 0 and there we have 1. Here we have 0 and there we have 1. And now we need to decide in which direction they point actually. So I'm going to let them point in these directions, meaning on this side I have an output of 1 and on that side I have an output of 0. Okay, now you can think for a moment. I have now these 4 segments or 4 polytopes, and you can think for a moment, where they will be mapped in my new diagram. Yeah, so I'm going to give names to these regions. Let's call them here A and B and C and D. All the points in region A, they are 0 according to my green perceptron. They are 0 according to my red perceptron. So everything, I could have called this one here the green axis. This would be Z1, and that would be the red axis, Z2. And all the points in this region A get mapped here. They get mapped to 0, 0. Yeah? Now all the points in region B, they get a 1 along the first perceptron or along the first axis. They get a 0 along the second axis. So all my regions B, all my points in region B, they end up here. And all the points in region D are here. And all the points in region C get mapped here. And now I have not drawn the label here, but this region A, in this toy example, those were all from the class cross. So I could, I have my cross class here, and I have the circle class there. Yeah. Yes. Great question. The question was, this is a Heaviside step function, and how are we going to train this thing? Yeah, and with Heaviside step functions, it's basically untrainable. We would need to try out all parameter combinations, which is why we're not going to use it in practice. But if I used not the Heaviside, but something smooth, my plot would become a lot more complicated. Yeah? So this kind of more complicated plot, I put it in the in today's OneNote document. In the document, you will see a plot where this kind of embedding is shown on the one hand for the Heaviside, but also for smoother versions thereof. But here this makes my argument simpler, yeah? And we will talk about numerics next time. Okay, so okay, I'm going to use the final color that I have. So all the crosses, all the region A was mapped here, and all the circles B, C, and D were mapped here, here, and here. And now we want to separate them. So I could now introduce a classifier in this region. And for example, let it point here. And then I say, okay, if this final perceptron outputs 1, this must be region A, this must be a cross, and if it outputs 0, it must be the other classes. So we have, again, some multipliers. In this case, the multipliers, this is a normal vector here. In this case, the multipliers are -1 and -1, and we have a bias. And the bias here, I think, would be positive, like +1 or so. And we send this through our step function once again. And then we finally get this output here. All right, so this would be our very first classifier, untrainable because we use these step functions, but it is composed here of 3 of these units. So this would be our first multilayer perceptron. All right. Any questions so far? So the direction in which these normal vectors point, those correspond to the weights on my axes. The bias tells me how this is shifted parallel to the normal vector. And in our case, our simplistic activation functions just map to 0 or 1. All good. All right. Then in the course of today, I mainly want to share 2 ideas. The first one is the so-called projection trick. which in the context of neural network, I would translate as width is good. And I'm going to construct a different toy example, because here, we started with 2 dimensions and we continued with 2 dimensions and it worked fine. Yeah. So this just showed that a concatenation of more than one perceptron or a composition of more than one perceptron can solve problems that a single perceptron cannot. Yeah? But now I want to use a different training example where we really inflate a dimensionality. And here I'm going to make this one-dimensional. So let's say we have our class cross, and then we have our class circle, and then we have the class cross again. And so it's just a one-dimensional feature space. And let's see if we can solve this with more than one perceptron. Yeah, if we can use this kind of construction. So we start with, in the diagram, we start with our single feature X, and we end with a single classifier that gives us our prediction for the label. And in between, let's see if in between using 2 perceptrons this might work. Yeah? So we would have one perceptron, we would have another perceptron. We have a bias term. Okay, good. Yeah, please experiment a little. Take 5 minutes or so, maybe less, to see if you can sort this out, if you can find the parameters, if you can find the multipliers here. To solve this problem, let's put the 0 here in our coordinate system. Please take your time, talk to your neighbor if you like. Talk to your neighbor, it's better. And then we can discuss how to solve this. Right. So somebody has a suggestion. Yes, please. Like so. Fine, but we have only a single feature right now. Yeah, so I cannot do anything at an angle. I can only cut orthogonal to the line because we only have a single feature. So I cut orthogonal, fine, and you wanted them to cut like here and there. Yeah, okay, good. So we cut here and say this is the green one, and we cut there and say this is that one. All right, good, but now we need to parameterize. Anybody has suggestions on how to parameterize? Yes. We could. Okay, the weight here is -1. That means it points in this direction, yeah? So I have 1 on this side and 0 on that side, okay? And on the other one, +1, so it points in that direction. We have a 1 here and a 0 there. This is the bias, yeah? And that's how much the bias is? Yeah, there's no scale here, but it needs to be negative, right? Because it's on the right-hand side of 0. So if we pretend that here, this is at a distance of +1, then the bias here would be -1, yes. And the bias here would be 1 times 1 would be +1, yes. All right. And then you used Heaviside step function, okay. And we can make this new plot. We have the green axis, we have the red axis. Can again call these intermediate ones here Z1 and Z2, Z1, Z2, 1, 1. All right. And now these get mapped. Yeah, so these get mapped here. Let's call this the region A. A gets mapped here, okay. And then B has a 0 from either side, yeah? So B gets mapped there, and C has 0 from the first and 1 from the second, so Z gets mapped here, okay. Now we have a picture very much like the one over there, and then we can use our second layer. Okay. Yeah, let's just do the numbers. Doesn't matter in which direction it points. So if we let it point in this direction, then the weights or the multipliers here would be +1, +1, and the weight would, the bias would be -1/2 or so. Okay, and then we have a perfect classification result. Good, so, you know, this was good. So this was very similar to what we've done here, but the important thing is the following. Here, for our input, we had the dimensionality p = 1. And here for our latent, we had, in this particular case, p = 2. So we had an intermediate or a latent dimension which was bigger than the input dimension. And what we have done is, and this is what the projection trick is all about, we have projected non-linearly to a higher dimension. A higher dimension in which the problem, even if it was not linearly separable in the input domain, in which the problem does become linearly separable. So this is the essence of the projection trick. And now we can think about how far we can push this projection trick. So, you know, think about the extreme case. What if the dimensionality of the latent space is equal to the number of samples? The number of training samples. Okay. Again, take a moment to think about a geometric argument that you could make. So we have we have n points in n dimensions, will we be able to classify them or to separate them linearly no matter what the label assignment? Question to you. Please take a moment to think about it. All right. So let's see. Does somebody have a geometric argument? And I did not say explicitly, I'm talking about two-class classification problems, yes? It is correct. And can we make a simple proof somehow, simple geometric proof? It's a true statement. Yes. Can you give an argument? Yes. Okay. So you are thinking about the samples lying in one dimension, and you say we put a decision boundary between each and every one of them, and then we map them to the corners of a hypercube because it's always 0 or 1. But these corners or this hypercube will have, if we have n samples and here n-1 or n decision boundaries, it will have n dimensions. But now, if we admit any permutation of the labels, how can we guarantee that it's always linearly separable? I think we have not made the argument quite yet.
We can make always a decision between these two, and then we zoom out a little bit, and then we have another cluster where we have them separated, and then we can make a decision between these two. So we just need a very deep and very wide perceptron, and we can always find one that matches all of it.
Maybe, I'm not sure I got it. What did you want to say?
Classifiers between all of them and point them all to the right. We could tell exactly from the left to the right how many of those are showing 1, and introduce increasing biases with perhaps opposing signs for each further input to flip the sign of the output. Each step
Again, I say maybe because because I didn't quite get it, but maybe, yeah. I'm telling you the argument I have in my mind. So let's say I have 3 samples in a 3D space. So these are just 3 points in a 3D space, and I can always fit a plane through, so if I have 3 points in 3-dimensional space, I can always fit a plane through these. And if I have 4 points in 4D space, I can always fit a plane through those, and so on. Yeah? And now in this space, I did not yet indicate the label. Yeah? So this could be class 1 or class 2. This could be class 1 or class 2. That one could be class 1 or class 2. And now the thing is, if we can always, for n points and n dimensions, if we can always perfectly fit a plane, and now imagine I throw a dice or a coin for each single training observation to decide what is its label. Yeah? So the labels are truly random. And then I tilt my plane ever so slightly, such that, you know, let's say class 1 is always above the plane and class 2 is always below the plane. Yeah, because my plane has a normal vector. It has a normal vector, which I'm trying to show like so. That would be the normal vector. And then I tilt the normal vector ever so slightly so that all the labels from class 1 are above and all the labels of class 2 are below. And this construction works as long as the points are in general position. Yeah? So as long as they as long as there are no subsets of points which are linearly dependent on each other. Do you find that a valid argument? Okay, one person thinks so. Thank you. Yes? Exactly. Yeah, this is the thing, the general position. That's exactly what you were saying. Yeah. Mm-hmm. Yes? Yes. This plane, in this example, would be this line here. Now here, you know, we have many points in 2 dimensions, so the picture does not work. But I'll give you a 2D example. Yeah. So So let's say I have just a 2D space, and I have 2 points, and I have not yet decided what is their label. I'm fitting a plane through these points, and now I'm throwing a dice. And for example, if I decide by throwing my dice that this is class 1 and this is class 2, then I will tilt my decision boundary a little bit, such that class 1 is above the plane and class 2 is below it. If I had thrown my coin such that this is class 1 and this is class 1, in this case, I would have needed to change the bias a tiny little bit. And I can repeat the same argument for any set of labels that I decide randomly. The thing that I do need is that the points are in general position. Yeah, so it fails when, okay, now I add a third point. Okay, or I need to go 1 dimension higher. I need to go 1 dimension higher. So I again have 3 points in 3 dimensions, but this time the 3 points lie on a straight line. So they are linearly dependent. And now if I create labels class 1, class 2, class 1, then by wiggling any plane that I fit through these points, I can no longer satisfy this labeling. Yeah, so I need them to be in general position. And the moment that they are in general position, this works, yeah? Because now I can find a plane that satisfies these labels. Okay, I will write this finding in words, and then we can have a break. So the question was, what if the dimension of the latent space is same to the number of samples? Will we be able to linearly separate always, regardless of which sample has which out of 2 labels? And the answer is yes. And the justification is can always fit a plane through all points. And if these points are in general position, so technical term, general position, they must not lie on a subspace, or no subset of them must lie on a subspace. Then non-technical term, then we can wiggle our plane or our perceptron to satisfy any 2-class labeling. And this requirement for general position here means that the mapping which we do, the mapping to this higher dimensional space that we're using, it must be nonlinear. Because if it were not, if we just took a linear transformation, so if we just take our samples X and multiply them with some weight matrix, that would not do the job. Yeah? Because this would, for example, if we start with 2-dimensional samples, and then I map them to some higher dimensional space, so let's say this is a Q times P matrix where Q is larger than P. The points would still lie on a two-dimensional subspace in there. Yeah. So this is why it is essential that we have a nonlinearity. Good. And now what this argument given here. So first, is this argument fine with everybody? Yes? Yes, if the points are in general position. Yes, can always if. That's really important. Yes? Yes. Yeah, that's enough. Yes. And did you have a comment or question? Okay, good. So in this argument that we've given now, this was just one point on the so-called function counting theorem, which I used to prove in past years, but I'm skipping it this year. The function counting theorem looks at the fraction of linearly separable two-class label assignments. And this is assuming, yeah, all right. And if we put here P over N, we have just argued that for P over N equals 1, we are up here. Yeah. So if our number of points are if we have as many points as we have dimensions, then we're going to be able to separate all of them. Yeah, so 100% we are here. If the dimensionality goes to 0 and we have many points, we are not going to be able to separate most label assignments. Yeah, so for example, in one dimension, the kind of label assignments that we can separate is a very small subset, namely only the ones where we have one class on the one side and the other class on the other side. So that's, as we make P and N large, this is going to be approximately 0. Yeah? And now the function counting theorem says that for P to N large, we get a step function here. Yeah, this is the essence of the function counting theorem. We get this curve here. For Pn going to infinity. And for finite values of P and N, this curve here is getting more and more, well, softer and softer. It's also a discrete curve because, you know, for small numbers P of N, I cannot have any fraction. Yeah, so this is really a discrete curve, but it looks broadly like so. Yeah? And so this case we have argued, this one we have argued on this blackboard, and the function counting theorem gives you the full story in between. All right, so the summary of this part is that the projection trick allows us to make any problem linearly separable if only we add enough hidden, if we only add enough perceptrons in the hidden layer. Or in other words, width is good. Okay, we have a 15-minute break, after which I will argue that depth is better.